In 2022, an unmanned underwater vehicle descended to a depth of 1,500 meters in the central Pacific Ocean, over the coordinates of the underwater volcanic chain known as the Northwest Hawaiian Islands. What it recorded during those hours of exploration not only changed the scientific understanding of active underwater volcanoes, but also alerted seismologists and geologists worldwide to a risk that had been underestimated for decades. The data collected by this underwater drone, operated by the Schmidt Ocean Institute team, revealed a system of hydrothermal vents directly connected to the magma chamber of the Kamaʻehuakanaloa volcano, formerly known as Loihai, whose activity now constitutes one of the most important seismic monitoring points in the Pacific Ocean. What they found was not merely fascinating from a scientific perspective. It was, according to the researchers themselves, a warning about geological processes that current models cannot yet predict with sufficient accuracy. Like, subscribe, and share. Let's begin. Submarine volcanoes account for roughly 75% of all volcanic activity on the planet. The vast majority are located at mid-ocean ridges, those enormous underwater mountain ranges that run along the ocean floor like seams on a baseball. But hotspot volcanoes like Kamaʻehuakanaloa are different. They form on plumes of molten material that rise directly from Earth's mantle, pierce the oceanic crust, and create volcanic structures independent of plate boundaries. This makes them unique natural laboratories for studying Earth's internal dynamics, but also sources of seismic risk with characteristics that standard earthquake prediction models don't fully incorporate. The drone that landed on Kamaʻehuakanaloa in 2022 carried high-precision sensors capable of measuring temperature, acidity, dissolved gas concentrations, and seafloor deformation. What those sensors recorded showed levels of degassing and thermal expansion significantly higher than those of previous measurements taken on the same volcano in 2014. Outgassing is one of the most relevant phenomena for understanding the seismic risk of submarine volcanoes. When magma rises from the volcanic chamber to the surface, it releases dissolved gases, primarily carbon dioxide, sulfur dioxide, and water vapor, through cracks in the seafloor. This process, called volcanic outgassing, produces changes in the pore pressure of the surrounding rocks. These pressure changes can destabilize pre-existing geological faults and, under specific conditions, trigger earthquakes. The Schmidt Ocean Institute team documented that the hydrothermal vents recorded by the drone showed significantly more intense gas flows than in the volcano's historical records, suggesting an increase in the pressure of the underlying magma system. Seismologists at the Hawaiian Volcano Observatory, who continuously monitor the activity of Kamaʻehuakanaloa, confirmed shortly afterward that the drone data matched an increase in seismic tremors recorded at the base of the volcano during the months prior to the mission. The relationship between submarine volcanic activity and earthquakes is not new in the scientific literature. One of the most studied cases is that of the Campi Flegrei volcano, located beneath the Gulf of Pozzuoli in Italy, whose hydrothermal activity has been directly linked to seismic swarms affecting the Naples region. But in the case of Pacific hotspot volcanoes, the dynamics are more complex because the oceanic plate on which they sit is constantly moving over the heat plume, creating a sequence of successive volcanoes that extends from Hawaii to the submarine chain reaching Midway Atoll. What the drone recorded in 2022 was especially relevant because it showed that the volcano's activity was not uniform across its entire surface, but rather concentrated in a specific sector of the northwest flank, precisely in the direction in which the Pacific plate is moving. That detail was not overlooked by the geologists who analyzed the images. It indicated that the interaction between the heat plume and the moving plate was generating structural stresses in an area that until then had not been considered to be at high seismic risk. The technology that makes this type of exploration possible has advanced remarkably in the last 20 years. The remotely operated vehicles, known as ROVs, used in the early decades of deep oceanography, were bulky systems with limited sensory capabilities. Today's underwater drones operating on scientific missions like the one by the Schmidt Ocean Institute are a completely different generation. Compact platforms equipped with high-definition cameras, multi-beam sonar, mass spectrometers capable of identifying the chemical composition of hydrothermal fluids in real time, and autonomous navigation systems that allow them to maintain position on the seabed with centimeter-level accuracy, even in the presence of deep currents. This technical capability is what allowed the 2022 team not only to record the presence of hydrothermal vents, but also to map their spatial distribution with a resolution that previous measurements, made with less precise equipment, had not been able to achieve. The detailed mapping of Kamaʻehuakanaloa's northwest flank, produced by that mission, revealed something no geological model had predicted: a network of secondary fractures radiating from the main hydrothermal fissures in a pattern reminiscent, according to the team's researchers, of the conjugate fault system that typically precedes the rupture of a major fault. This pattern, documented in terrestrial seismology studies as a precursor to moderate to high magnitude earthquakes, Submarine volcano with the level of detail that the drone's sensors made possible. The significance of this finding extends beyond the specific case of Kamaʻehuakanaloa. It suggests that active submarine volcanoes may be significantly underestimated sources of seismic hazard in current risk maps, which are mostly built on surface volcanic activity data or historical seismic records, without incorporating the kind of structural analysis of the seafloor that only direct exploration with precision drones makes possible. Like, subscribe, and share. Researchers from the Schmidt Ocean Institute published their findings in the journal Earth and Planetary Science Letters in 2023, and the article's conclusions were picked up by specialized geophysics publications worldwide. The article put forward two main hypotheses about the meaning of the observed degassing and fracturing patterns. The first suggested that the volcano was in an inflationary phase preceding a submarine eruption, a process that could last for decades, but that at some point during that period could generate earthquakes of significant magnitude in the region. The second hypothesis, considered more likely by most of the study's co-authors, proposed that the observed patterns reflected a structural reorganization of the volcanic edifice related to the movement of the Pacific Plate, a process that would not necessarily culminate in an eruption, but would generate recurring earthquakes of moderate magnitude at the base of the volcano over the coming decades. Both hypotheses agreed on one point. The activity recorded by the drone in 2022 indicated that the system was far from the state of relative quiescence that the records of the previous decade had suggested. What these findings mean for the scientific community and Pacific risk management authorities is one clear conclusion: active submarine volcanoes need continuous monitoring with direct exploration platforms that go far beyond seismic detection systems installed on land or on the seabed. Seismic records are indispensable tools, but they are indicators of a process already underway. Drones capable of mapping seafloor deformation, the distribution of hydrothermal vents, and degassing patterns in real time offer something different: the possibility of detecting the buildup of structural stresses before those stresses are released catastrophically. The Kamaʻehuakanaloa eruption in 2022 demonstrated that such early detection is technically possible. The question researchers now raise is whether the resources allocated to the systematic monitoring of submarine volcanoes in the Pacific, Atlantic, and Indian Oceans are sufficient to apply this capability at the scale that the actual risk demands. The answer, according to most of the scientific community, is not yet, but the technology to do so already exists, and missions like the one that recorded the fissures of the Kamaʻehuakanaloa volcano in 2022 are paving the way for an understanding of oceanic seismic risk that could, in the coming decades, radically transform how the world monitors and anticipates earthquakes originating from the depths of the ocean. The science behind these findings is also transforming how ocean geology is taught at universities. For decades, submarine volcanoes were treated in geology courses as geologically important but seismically secondary phenomena compared to major subduction zones like the Cascadia subduction zone in the northwestern United States or the Nankai subduction zone in Japan. Data accumulated over the past 10 years by direct exploration missions are changing that hierarchy. The North Pacific Seafloor Observatory, a network of instruments installed on the ocean floor off the coasts of Oregon and Washington, has recorded multiple seismic sequences associated with volcanoes on the Juan de Fuca Ridge during that period, sequences that were not previously considered in coastal hazard models for the region. And in the Mediterranean, studies of the Marsilli submarine volcano, located off the coast of southern Italy and considered the largest submarine volcano in Europe, have revealed that its internal structure is significantly more unstable than previous models indicated, with a potential risk of flank collapse that could generate a tsunami with serious consequences for the coasts of Italy, Tunisia, and Algeria. These cases reinforce the central message that the drone that landed on Kamaʻehuakanaloa in 2022 brought back to the surface. The ocean floor is not a static or silent place. It is a dynamic system whose activity has direct consequences on the planet's surface, and understanding it with the depth that the risk demands requires precisely the kind of direct exploration that this mission represented. The future of oceanic, volcanic, and seismic monitoring necessarily involves expanding fleets of underwater drones with advanced scientific capabilities, deploying permanent sensor networks on the most active ocean floors, and developing computational models that integrate direct exploration data with real-time seismic and geodetic records. Several international projects are currently working in this direction. The Smart Cables Program, promoted by the International Telecommunication Union, the UNESCO Intergovernmental Oceanographic Commission, and the World Meteorological Organization, aims to equip seafloor fiber optic cables with seismic and oceanographic sensors that transmit real-time data from the most remote points in the ocean. If this project reaches the scale its promoters envision, the world will have an unprecedented seafloor observation network within the next decade, capable of detecting the accumulation of stress in active submarine volcanoes before that stress translates into earthquakes or tsunamis. What a drone recorded at a Pacific volcano in 2022 was much more than a local scientific discovery. It demonstrated that the technology needed to anticipate some of the planet's most dangerous geological hazards is already in our hands. What's lacking, as so often in the history of science applied to human safety, is the will to use it on the scale the problem demands. Like, subscribe, and share. Until next time.